We've been discussing the multigrid method and how it's based on this coarse grid correction scheme whereby we go between finer and coarser grids in order to accelerate an underlying relaxation scheme such as Gauss-Seidel or ADI. We've discussed the specifics of how we define the grid in order to go between the various grid levels. We also looked in the previous video at how to apply the boundary conditions on the various grid levels as well. In this video, I want to discuss the relaxation schemes, the restriction and interpolation operators, as well as how we deal with nonlinear elliptic equations using the multigrid method. So remember that the point of the multigrid method is to accelerate an underlying relaxation scheme. It could be Gauss-Seidel, it could be ADI. I'll discuss both of those here very quickly. In order to implement these on a parallel computer, we need to worry about data dependencies. We would use what's known as red-black Gauss-Seidel iteration. Red-black in the sense of a checkerboard, where every other segment on the checkerboard is red-black, red-black. So for example, if we have our grid lines as you see here, every other point would be red or black, as you can see. And the reason for doing that is if you look at, say, a black point right here, the north, south, east, and west points that are part of its 5-point finite difference stencil, you notice that doesn't involve any other black points. It only involves red points. So we can do the red points in parallel, the black points in parallel, and there's no data dependencies between them. But again, it's just basic Gauss-Seidel. Notice you would not use the SOR. The multigrid technique itself is doing the acceleration. There would kind of be a tug of war between them. And just as we said that alternating direction, or the ADI method, is more elliptic-like and better because of that than Gauss-Seidel, the same is true within the context of the multigrid framework. Just like with red-black Gauss-Seidel, we could do what I call zebra relaxation, whereby we do every other line. And in that way, again, eliminate any data dependencies. Otherwise, it's just like regular ADI. We're just doing it on these smaller and smaller, coarser and coarser grids, and then going back up through the V cycles as we discussed in previous videos. So let's move on to the restriction operator. Remember the restriction operator? It takes information from the fine grid, the H grid, to the coarse, or the 2H grid. So we'll define the coarser grid with the indices ij, I going from 1 to capital N sub x, j going from 1 to capital N sub y, and then on the fine grid it's the same ij, n sub x, n sub y, but we'll put stars on them to indicate that they're the finer grid. So as we move through the grid, which grid becomes the coarser and the finer, of course, changes as we go up and down through the V cycle. Then the relationship between the n sub x and n sub x star is as follows. We looked at this in the last video in terms of defining the grid. So if you have a fine grid, nx star, you subtract off 1, take a half, add the 1 back, and that gives you the number of points in the x direction in the next coarser grid, removing every other point. Same thing for y, and then I star is just 2 times I minus 1. Same thing for j star. So the easiest way to implement restriction would be simply to remove the information at every other point. So we take the fine grid, take every other point out, and now we have a coarse grid. That's called straight injection. So the uij and the ui star j star are just the same on the coarse and the fine grids. And you simply throw away all the additional information at the points that have been removed. Now this is not ideal because you literally are throwing away valuable information that you know from the solution on the fine grid and not using that when you restrict to the coarser grid. So the more popular approach is what's called full weighting. Let me start over here on the right. So this is a segment of our grid. Here's the ij point and the I star j star point. The point to the right on the coarse grid would be I plus 1j. The point above would be ij plus 1. You'll notice it's 2 delta x's to the right, 2 delta y's above. And then the fine grid points, which are separated by delta x, delta y, and you can see those with the starred indices. So the same I star j star corresponds to ij, and then I star plus 1, j star, and so forth surrounding this. The way the symbol on the left works is this gets superimposed onto the grid on the right. This center point corresponds to this. It's the weighting factor for this point, and then the corners, for example, those correspond to these corners. and then the values in the 3 by 3 matrix here that represents the symbol, those give the weighting factors for each of the points. So we take 1/4 of the I star j star point, we take 1/8 of the north, south, east, and west points, which are these 4, and then we take 1/16 of the corner points, which are these right here. Okay? So as you can see, the further away you get from the center point, the smaller the weighting factor. These weighting factors are not arbitrary. They come from interpolation theory. So then Uij on the coarse grid, so the value here on the coarse grid, is then 1/16 of those 4 corner points, plus 1/8 of the 4 north, south, east, west points, plus 1/4 of the center point. And then you just shift this template through the grid in order to do the restriction at every value on the coarse grid that we're moving information to. Then the interpolation or prolongation operator, where we're taking information from the coarse to the fine grid, and we want to fill in the values on the fine grid that do not correspond to points on the coarse grid. So again, if you look on the right here, here's the ij point, now in the lower left-hand corner, corresponding to the I star j star point. And then the next point to the right on the coarse grid is I plus 1j, above I, j plus 1, and then the upper right corner, I plus 1, j plus 1. Then the fine grid points fill in halfway between. So let's take this part of that subdomain. So we know the values here, 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 and here on the coarse grid, and we need to fill in the values here, here, and here. We're just going to copy the values on the common points. So I star j star will just be the same as the value at ij. You see that here. And then how do we get a value here, here, and here to fill in the remaining fine grid points? So from the symbol on the left, we're going to take this portion right here. And that gets superimposed here. So the 1 corresponds to the ij point. The 1/2 corresponds to the I star plus 1 j star point. Come back to that in a moment. This half corresponds to this point, and 1/4 corresponds to this point in the middle. Now why the 1/2 and the 1/4? This is just linear interpolation. So if I wanted to get the value here, I just take the average of these two values. If I want to get this value, I just take the average of these two values. That's what's reflected here and here. 1/2 of the sum, 1/2 of the sum of those two. And then this point in the middle, well, that's just the average of these 4. So it's 1/4 of the sum of those 4 points. And in that way, we fill in these 3 additional points that correspond to the fine grid. And then again, we shift this template through the grid to fill in all of the fine grid points from the information on the coarse grid. So let's make some remarks about this. You'll remember that I keep describing the multigrid method as really a framework. It's not so much a method as it is a framework that's wrapped around an underlying relaxation technique. So Gauss-Seidel is the most popular. We also discussed the possibility of using ADI. So we basically have these ingredients. We have the relaxation, we have restriction, we have interpolation. We combine those together to form the coarse grid correction scheme that makes up the V cycles. This is a very complex technique. It's a very cumbersome framework to program, so it better be significantly faster than the underlying relaxation technique that we're trying to accelerate. It turns out that it's comparable in speed to the fast Poisson solvers, which are also quite complex. The key, however, is that whereas the fast Poisson solver has significant limitations on the differential equations they can be applied to, namely they need to be linear and at worst have variable coefficients. In the case of multigrid methods, we can extend them to nonlinear equations and still have speeds that are comparable to the fast Poisson solvers. So this additional flexibility is really the key to why multigrid methods are so commonly used and so popular. Now, as is almost always the case, there is a cost. To improve the efficiency, the computational efficiency of these underlying relaxation techniques, there is a cost. One clear cost that we've seen already is that there's additional programming complexity involved. So the programming itself is going to be much more complex. Now that's just a one-time cost to write the code in the first place. In terms of running the code, what is the cost? The cost in terms of running the code is that we'll basically have to double the amount of memory that's required. And the reason for that is because we need to store information on every single grid. Now, each course or grid only has half as many points in each direction, so 1/4 of the points if it's a two-dimensional problem. However, we still need to store all of that information. So if you add all that up, that's roughly twice the amount of storage required to solve the problem on the finest grid using the underlying relaxation technique. Now, that's usually a good trade-off today because memory is abundant and cheap as compared to CPU speed, which is generally speaking expensive. And so if I can trade off some computational time on my CPU or GPUs for memory, that's generally speaking a good trade-off. And as I've been implying, because of the speed and generality, these multigrid methods really are the current preferred framework for solving elliptic partial differential equations, including nonlinear PDEs such as the Navier-Stokes equations that I'm solving every day in my computational fluid dynamics research. And we'll talk about the nonlinear equations and how we treat those using multigrid methods in the next section. Historically, we give credit to Aki Brandt in the 1970s, who developed this framework. He actually did not call it multigrid, he called it a multi-level framework. But actually, there's some work in the 1960s by some Russian authors who predated Aki Brandt and laid the groundwork for this multigrid framework. All right, so let's see how we can extend this multigrid approach to nonlinear elliptic equations. It's basically the same structure going through the coarse grid correction. However, there's some changes that we need to make in order to accommodate the nonlinearity of the differential equations and the corresponding difference equation. So we still have our L operating on U hat is equal to F. L is the difference operator, and that represents our difference equation. We still define the error as the difference between the exact and the numerical solutions. We have the residual, which is F minus LU, where L is operating on the approximate numerical solution, and so the residual tells us how wrong that solution is. So that's all exactly the same. There's nothing new. What changes, however, is because of the fact that our difference operator now is nonlinear, we can't substitute this definition of the error in the same way as we did before because of this nonlinearity. So let's see how it's different. We still start with LU hat is equal to F, our difference equation that we're trying to solve. Before, you remember that we changed this to an equation for the error E, and it was LE is equal to R being the residual. Here we can't do that because the difference operator is not linear. We can't just split it up in that same linear fashion. So instead, let's write the F on the right-hand side, which from back here, that's just equal to LU plus R. So let's put LU plus R on the right-hand side. So we have LU hat is equal to LU plus R. So the difference now is instead of just restricting the residual from the fine to the coarse grid and then using that as the right-hand side of our error equation to relax on the coarse grid, we now need to restrict both the residual R as well as the approximate solution U, because we have both R and U that we need to restrict from the fine grid to the coarse grid and then solve on that coarse grid. So we're going to modify that coarse grid correction procedure that we had before. It's generally speaking the same coarse grid correction scheme. However, the second and third steps have to be modified slightly because of this change. All right, so here it is. The first step is exactly the same. We relax on the original difference equation, LU is equal to F, a certain number of times on the finest grid. The second step is now slightly different. Remember before, we would calculate the residual on the fine grid. We would restrict that residual to the coarse grid and use that on the right-hand side of the error equation. So we do that here as well, but we also need to restrict the solution U itself. So we have the solution U on the fine grid. We use the restriction operator to restrict that down to the solution on the coarse grid. So now we have the residual and U on the coarse grid. Then in step 3, we consider this equation. Again, before, that was the error equation in the linear case. Now it's this equation, LU hat is equal to LU plus R. So I know everything on the right-hand side in step 3, and so I can solve this, quote unquote, for U hat. We don't actually get the exact solution because we're going to recursively do more coarse grid corrections, but we're pretending as if we're solving for U hat. Once I have U hat, the difference between U hat and U, that's the error. I can then interpolate that error up to the fine grid. Here's the error on the coarse grid, interpolate it up to the fine grid, use that to correct the solution UH on the fine grid to get a new solution on the fine grid. And then step 5 is the same as before. We relax on LU is equal to F on the fine grid a certain number of times in order to complete the coarse grid correction. And then we again put this into context of a V cycle. We do the V cycles as many times as necessary until we get a converged solution. This is called full approximation storage, or FAS. And that's because we now have to store both the solution and the residual as we go up and down through the grids. Now you notice that the difference equation that's being relaxed is for the dependent variable u hat, that was in step 3, and not the error, as was the case before. And this is what I said in the earlier video. You think of these functions, the restriction, the interpolation, and relaxation, as being general functions that you can apply on any input. So you can relax on the error, you can relax on u hat, you can relax on whatever you want. You can restrict the residual, you can restrict the solution, you can restrict whatever you want. Same thing with interpolation. Now to actually linearize the nonlinear terms in our difference equation, we use Newton's method, which we'll discuss in the next video. We can also use the full multigrid method in order to get a good initial guess before we start our V cycles. And we can do V cycles, as we've discussed, or what are known as W cycles. So how many times you go down, how many times you come back up before you go down. You can devise a number of different combinations of those and get V cycles, W cycles, and whichever one is the fastest is the one that you use. But in any case, the coarse grid correction sequence is the same as before, that we use recursively to get these V or W cycles. The only difference is that second and third step in the coarse grid correction scheme.